Thank you, Mr. Chairman. Well, I don't like this mic, so if you can't hear me, then tell me, but I usually speak so loud that usually people hear me in the room. So my name is Vodička, and I'm going to talk about the phase field model of fracture, which includes also interfaces, and which also includes the inertia in the model. The sketch of the talk is written here, and to start with some snaps that show how the model is, for which cases it is applied. I show them to see that the interfaces are related to the inclusions or inhomogeneities in the interface, and that the stress state in such structural elements can be any complicated, that may include any mixed mode loading, any type of compression loading, which is also some important part to demonstrate in this presentation. The model itself for the interfaces uses so-called model of adhesive contact, which together with the variation model of fracture expressed by the phase field method of fracture includes also the dynamic effect. Here are the list of some interesting references related to that topic. Due to lack of time, I go directly to the description of the model, which is expressed in terms of energy, as it is a variational model. So I start with a description of the strain energy, which when we talk about the complicated stress states is usually expressed in such a separated form when, for example, here we use a split of strain into spherical and deviatoric parts to distinguish, for example, tension and shear. Well, of course, the model may also include some kind of rheology, but it is not important in this explanation for today. But what is important is the energy related to cracks, which introduces fracture energy, here related not only to bulks, but also to the interfaces. When with the phase field model, we replace those integrals also on the interface by regularized integrals, which instead of having unknown contours, unknown cracks, introduce new additional variable in damage fashion, which is called either phase field damage parameter or interface damage parameter. So we have these two regularization, which have a very similar form. At the interface, this model is related also to this adhesive, which we can imagine as a thin layer of springs, so that it adds some energy due to those springs. And having that damage form, the material is degradation. Also, interface is degraded. So we introduce those degradation function phi, capital Phi or small phi in the interface and in the bulk. Well, actually, the form of those function is described in literature. Particular form here is not so important. Well, another ingredient into energy summary or energy balance is the energy of the external forces. For inertia, we have the kinetic energy. And of course, we may have some dissipation, either due to that rheology, which I mentioned before, but what is important for us also due to some other processes which are related to crack formation processes. Here it is denoted, this influence by this function GC, which defines some kind of mode mixity and which also makes possible to introduce that influence of compression. It should be said that the whole process is unidirectional, which is expressed by those unidirectionality conditions, and which make this dissipation potential thermodynamically consistent. Okay, so what about that function GC, which again relies on that split of the strain, as those spherical part in tension are usually related to the mode 1 of the crack, which is here related to GC1 for mode 1. The deviatoric part is related to the shear mode. Then we may have different energy needed to propagate the crack. And it may be, when it is compressed, affected by the level of compression. which introduces here another parameter denoted omega. This, in a similar way, we may done it in the interfaces, but there is no not the split to spherical and deviatory part, but we have normal elongational or compression of the spring and tangential of those spring at the interfaces. So to summarize that, we have for opening for this function GC1, which adds no additional energy because that was already included in the phase field or original phase field model. For shearing, we have additional GC2, so that there is additional energy added GC2 minus GC1. GC1 is from the previous part. And when we have compression, then energy may be even different from the pure shearing. Okay, so to describe the dynamic evolution, we may rely on Hamilton variational principle here, extended for the presence of the dissipative forces, so which say that the functional of action at the solution defines its stationary point, so that the condition of the stationarity are expressed by the following relations. The first two of them define the equation of the motion. The last two define the flow rules for the damage either in the phase field or along the interface. Naturally, it is equipped also with the initial conditions. So these are the conditions which are to be solved. It should be said that is also physically relevant because it can be easily shown that it satisfies energy balance. And we have the kinetic energy, potential energy, and then related to that time range 0 and t, we have the work of the external forces applied in the range 0 t and the dissipated energy in that in the same time range. Okay, now I spend a few words about the computational procedures used for solving that, because all calculations are made in an in-house MATLAB code. So at least to have idea how it works. First, we wanted to use the numerical solution for time discretization suitable for the first order equations in order not to have numerical attenuation. Thus, we needed to introduce velocity, and then the system is in displacement in displacement variable of the first order. And now we apply that numerical discretization, numerical time stepping using so-called Krag-Nicholson formula, which uses backward time difference and which uses the midpoint value, so that for the first relation for the velocity is given by the first relation and the substitution in the other relation is provided here. In relation to the solution of the problem, we use so-called staggered approach, which means that we separate solution in displacement and damage variables. It has an advantage that the problem, also in the numerical solution, keeps its variational structure, which means that when we backwardly substitute for the velocities from the first formula, we may see that in fact the first two, or the second and third relations, are conditions of the minimization of some functional. We know that it is stationary point, but according to other conditions, it may be shown that it's convex, so that's actually its minimum. Similarly, the last couple of the relations provide, again, under conditions, assumptions that are made that the solution is obtained as a minimum of this functional. So that those two minimizations are made in the staggered scheme in each time step up to predefined time range defined by capital T. Okay, the spatial discretization, I think, is clear. This is made by finite element method, so that after substitution of shape functions, we obtain some algebraic formula which can be solved by either directly quadratic programming algorithms with some constraints, or if some function like degradation functions are not purely quadratic, but they are defined to be convex. They may be approximated by quadratic functionals using Taylor series, and then the algorithm is applied sequentially. How much time?
4 minutes. 4 minutes.
Okay. So these are the details of the finite elements, not so important. The scheme of all calculation is written here. So we can see that first we have in each time step the quadratic programming within the displacement variables, and then the sequential quadratic minimization, which has an iteration within this damage variable and provides the other part of the solution at the nth here time step, and this is done in all time steps to obtain the solution. So I want to show some calculations. What I want to show is influence of the interface, so how it can affect the form and shape of the crack, and also how or which kind of cracks can be identified when the load is compressive. So first we have tension. Yeah, so I go directly to those cracks due to lack of time. So we may have, I would say, weak interface, so that the fracture energy is low, and the crack tends to appear directly on the interface, and then it may kink to the matrix. We also can observe at the right plot, where some measure of tension is shown, that it is actually dynamic, so there's this finite wave of propagation speed of the wave that goes through the material. Okay, so we can see that a crack appeared first at the interface and then propagates into the material. When we put it fracture energy at the interface larger, so that it cannot break, so that actually the location of the stress concentration is the same, so the material of the matrix breaks, which of course may occur in materials. So we can see that simulation. I would say that the material or material parameter related to cracking procedures are not taken for any real situation. I would like just to demonstrate various scenarios of crack propagation. Well, in compression, we can check those parameters. The first case, yeah, we have GC2 and parameter omega. We can see how that parameter causes crack propagation. Again, we have a weaker interface, so that there appear a crack directly on the interface, and at the crack tip of that, there appear a crack in the matrix due to compression. When parameter omega is a bit larger, so that influence of the compression is less, then we can see that the crack appears more or less like for shear, so under 24 degrees below the same inclusion. Yeah, that's different angle of that case. So by that factor, the shape of the crack may be controlled, and the value of GC2 related to GC1 says how strong it is, how much energy is needed for crack to appear, to propagate. So for smaller value of GC2, that may be a different location of the crack, because for smaller time, when we have proportional loading, there may be sufficient energy for the crack to propagate also here earlier in time. So we will see also that case, which is a bit complicated. I'm not sure how it works in reality. Finally, I would like to show a case with more inclusion and show how the quality of the interface affects the crack propagation. Again, we have two cases, a stronger interface and a weaker interface. In the first one, we will see no interface crack, only degradation of the matrix. And contrary in the weaker, we will see also the interface crack, in both cases in tension and also in compression. So this one is strong, so we have only material crack. Here we have also interface crack in tension. And now in compression, we have only material and also interface. So those material parameters can be adjusted according to real material condition to be in accordance with real situations which are expected to be measured in the near future in our laboratory. Well, I believe I am in time, and thank you for your attention.